Good afternoon, everyone. I hope that you're having a good week so far. What we're going to do today is finish off our work with permutations. This is lesson 30.23 part B, and it can be found on page 34 of your lesson handout. So as a warm-up, there are three questions we have to answer. The first question is, how many unique arrangements of the four letters of the word past are there? Unique just means different. Well, there's a number of ways that we could answer that question. If we go back to the fundamental counting principle, you are going to arrange four items. The number of choices you have for the first item is 4, and then 3, and then 2, and then 1. I would probably say, though, that you should know that when you arrange a number of items, the number of arrangements is that number factorial. But here's where things get a little bit different today. That's true as long as the letters are all different. If you were to try to come up with 4 factorial, which is 24, there are 24 different arrangements of all of the letters of the word past. If you tried to come up with 24 different arrangements using the letters of the word past, you couldn't do it. So if I gave you some Scrabble tiles, I gave you a P, an A, and 2 S's, and you started arranging all of those, you would never reach 24 different arrangements. And the reason why you can't is there are 2 S's that are identical. So if I decide to switch, for example, in the word past, if I decide to switch this S and this T, I get a different arrangement. I get pats. But if I decide to switch this S in the word pass and this S in the word pass, I still have the word pass. So what I've done is I've listed all 24 different arrangements of all of the letters of the word past. There they all are. No matter how you try to arrange those 4 letters, you're going to come up with one of these 24. Now what I'm going to do is I'm going to move to the next page here, but the T's are all going to become S's. So if you take a look at the top of the screen and focus on the word past, I'm going to change it to pass. That T is going to change into an S. And every single T in this list is going to change into an S. And when I do that, this is what I get. So how many different arrangements am I getting here? Well, I have pass, so I don't include this pass. I have PSAS, I have PSSA, I've already counted PSAS, I've already counted PSSA. I have ASSP, I have ASPS, so I already have ASPS, I don't include that one. I already have ASSP, I don't include that one. This is a tedious process. And we're going to come up with a rule which will be more helpful. I have APSS. I think many of you are going to see here that what's happening is because we've changed all of the T's to S's, we get pairs of identical arrangements. So for example, I have SSPA and I have SSPA down here. I have SSAP and I have SSAP down here. I have SASP, SASP, and I have a SASP down here. SAPS occurs in 2 places. So I'm only going to count it once because it would only be one particular arrangement. I have SPSA, and I have SPAS, SPAS. So if I count the number that I've drawn ovals around, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And it doesn't take a genius to see that it's 12. We didn't have to count them because everything was happening in pairs. We went from 24 to 12. Now the third question is, what if I asked you to arrange all of the letters of the word SAS? So if you take a look at the top of the screen here where it says pass, I'm going to move to the next page, and the P in pass will change to an S. And that means every P in my list will change to an S, and this is what I get. So I get the word SAS, but I'm not going to include it here. I'm not going to include it here or here or here or here. The word SAS actually appears in 6 places. ASSS appears here. Now ASSS appears in a number of different places as well. A total of 6. But I can only count one of them. Otherwise I've got identical arrangements and we're asked to find different arrangements. So if we check this out and you think about it, you're only going to have 4, because basically the A can be in only one of 4 places. You can have S, then A, then SS. You can have S, then A, then S. You can have S, 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 and then A, or you can have the A at the beginning. Everything else here, these are all just duplicates of those 4. So the answer to the question is there are 4 unique arrangements of all of the letters of the word SAS. This is what we've discovered. If you arrange 4 items that are all different, you get 24 permutations. If you arrange 4 items but 2 are identical, you get 12. And if you arrange 4 where 3 are identical, you only get 3. And there's a rule that we use for this. The rule is that you divide by a factorial of the items that are repeated. So, for example, when we were arranging the letters of the word pass, you would normally say it's 4 factorial, but we have to divide by 2 factorial because there are 2 S's that are identical. And if you take 4 factorial divided by 2 factorial, you will get 12. If we were talking about arranging all of the letters of the word SAS, then it's 4 factorial. But since there are 3 identical items, we're going to divide by 3 factorial. And you will discover that that will give you the answer we got, which was 4. And it doesn't matter how many different things are repeating. To illustrate, if I take the word Mississippi, and I ask you how many different arrangements are there of all of the letters of the word Mississippi, we would take, I believe it's 11 factorial. Let me count those letters. It is 11 factorial. And then we would have to divide by, well, let's see. I have a number of I's that are repeated. I have an I here, 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 and here. There are 4 I's. I need to divide by 4 factorial. I have a number of S's that are repeated as well. I have an S here. That's 1, 2, 3, 4. I have 4 S's. What does that mean? It means I have to divide by 4 factorial. And I also have 2 P's. So I need to divide, in addition to all of that, I need to divide by 2 factorial. So we're going to take 11 factorial. Now we have to divide by the product of 4 factorial, 4 factorial, 2 factorial. So I'm going to put a set of brackets there, otherwise I will not be dividing by all of those items. I didn't close the brackets, you don't need to. The bottom line is there's 34,650 different arrangements of all of the letters of the word Mississippi. If I could come up with an 11-letter word where all of the letters were different, and I didn't spend any time planning for this, so I'm not going to worry about it. If I arranged 11 items that were all different, then that would be the number of arrangements. So the bottom line is when you have repetitions, you have to divide by the factorial numbers of the things that are repeated. So number one, how many arrangements of all of the letters of the word calculus are there? I always like to just write this a little bit bigger. How many letters are there? 2, 4, 6. There are 8 letters, so you would normally say 8 factorial. And we are going to divide by, now here's where I think you can easily make a mistake if you don't write things on paper. Because if I write this on paper, then what I can do is I can start off on the left and say, well, I have a C. Have I got any other C's? Yes, I've got 2 C's, and that's it for C's, which means I'm going to divide by 2 factorial. And then what I do is I go to the next letter, A, and I move left to right, and I see there are no more A's. L, I move left to right, and I see there are 2 L's in total, which means I need to divide by 2 factorial again. Then I go back to the left-hand side, and I start at the next letter. I have 2 U's. It's just a way to keep things organized, which would be 2 factorial on the bottom, and then I have an S, so I'm done. So what this works out to is 8 factorial over, well, this is interesting. 2 factorial is 2. 2 times 2 times 2 is 8. This is going to work out to 7 factorial. Because the 8 factorial on the top here is 8 times 7 times 6, all the way down to 3 times 2 times 1. The bottom is an 8. So the 8's cancel, and you're left with 7 times 6 times 5 times 4 times 3 times 2 times 1. You don't have to write your answer as 7 factorial. It was just an interesting observation. The correct answer is, after all these years, I still don't know what 7 factorial is. 5,040. So this is our answer. The next question. We have 4 blue cars. So what I'm going to do is I'm going to write the blue cars by saying BB, BB. They're identical, so I'm going to treat these like the letters B. If I take the blue cars and I take 2 of them and switch their positions in a parking lot, I haven't created a new arrangement. So these are identical items. I also have 5 yellow cars. And then I have 3 red cars. And the first question is, how many ways can I park all of these vehicles in a line if there are no restrictions? Well, if I count the number of items, I have a total, I believe, of 12 items. And I do have 12, I was just counting them again. But 4 are identical. I can't tell them apart, the 4 blue cars. I have 5 yellow cars, and I have 3 red cars. And that's the answer to A. We'll calculate that in a minute. Now, what if the blue cars are all together? Well, if the blue cars are all together, then I'm going to treat that as 1 item. So what I really am arranging here, everybody, is this item and all of these items. So if I count how many items I'm arranging, I have a total of 9 items. I have 5 yellow, plus the 3 red is 8, plus the grouping of blue is 9. And that means that the number of arrangements is going to be found by, at least to begin with, writing 9 factorial. Then I have to divide by 5 factorial for the yellow, and 3 factorial for the red. Now, I'm not going to divide by 4 factorial for the blue because I'm not arranging those 4. I'm just treating them as one group. This is different than Joan and Emily having to stand together, where we would multiply by the number of ways to arrange them. So now we can calculate our answers. (12 factorial divided by, in brackets, 4 factorial, 5 factorial, 3 factorial, gives us 27,720. That's the answer to 2A. And 2B is 9 factorial divided by, in brackets, 5 factorial multiplied by 3 factorial, which gives 504. So 27,720 is our answer here, and 504 is our answer here. So there's one more thing I'd like to go over with you today. This is called a pathway problem, and Jillian is walking from her home to school. So she's going from the bottom right in this grid to the top left. And she is going to be walking along sidewalks. She's not going to be cutting corners. She's not going to be jumping over fences. She has to travel along these lines. And she also must always get closer to the school. Now, if she is always getting closer to the school, that means wherever she is, she can only move in this direction or in this direction. So, for example, one particular path that Jillian could take would be to start at home and walk up, over, up, over, up, and over. She could do that. That is a possible way for her to go from home to school. What she could do instead is start here and go up and over and up and up and over, 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 and up. And that's a different pathway. And what the question is how many different pathways are there? And I always kind of joke that this is the kind of problem that your junior high math teacher would give you just to keep you busy. Because if you tried to trace them all, you'd go a little bit batty. That's hard to figure out. So there is a very efficient way of figuring out how many pathways there are. Now, when we take a look at the pathway that I've created in pink, I could describe that pathway in pink by saying the following. U, U, L, 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 U, L, U, L. And as a challenge here, you might want to pause the video and see if you can figure out what these letters mean. What they stand for are up and left. Remember, I said that Jillian can only move in these two directions. Well, one of them is up and one of them is to the left. So when you take a look at the pink pathway, she travels up, up, left, 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 up, left, up, left. On the other hand, when you take a look at the blue pathway that she takes on a different day, she starts by moving up, then she moves to the left, then she moves up twice, then she moves left a total of 4 times, and then she moves up to finish her journey. Now let's take a look at each of these. When you take a look at the pink pathway, she makes 4 moves up and 5 moves left. If you count the U's in the pink pathway, there are 4 U's, and if you count the L's, there are 5 L's. It's interesting because if you count the U's and L's in the blue pathway, there's the same number of U's and L's. And when you take a look at the grid that she's walking on, that makes sense. No matter how she gets from H to S, she's got to make 4 moves up and she has to make 5 moves left. So what this question boils down to is how many different arrangements are there of these letters? Because each one of those arrangements will be a unique path. One of the arrangements is the blue arrangement. Up, left, 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 up. One is the pink one. Up, left, 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 up, left. Another one would be left, 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 up, up. Each unique arrangement is a pathway. So how many ways can we arrange these letters? Well, there are 9 of them, so it's 9 factorial. Divided by, we have 4 that are identical moves. They're up, so that's 4 factorial. We have 5 that are identical. There are 5 L's. That's 5 factorial. This is going to be the number of pathways there are. So 9 factorial divided by 4 factorial, 5 factorial gives you 126. There's 126 different ways for Jillian to get to school from home. And if you tried to trace them all, like I said, you'd go a little bit nuts trying to find them all. Now B, what is the total number of pathways from A to B? Well, to go from A to B, you have to do a couple of things. One of the things you have to do is you have to go from A to C, and you must go from C to B. This is exactly the same as saying Bobby Bear must choose a shirt and a pair of pants. To find out the number of ways Bobby Bear can get dressed, we had to take the number of ways to choose a shirt and multiply by the number of ways to choose a pair of pants. To find out how many ways to go from A to B, you have to take the number of ways to go from A to C and multiply by the number of ways to go from C to B. So how many ways are there to go from A to C? Well, from A to C, you are arranging right, 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 down, 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 down. You are arranging those 7 items. You need to make 3 moves to the right and 4 moves down. That means you're arranging 7 items, which is 7 factorial, but you need to divide by 3 factorial for the R's and 4 factorial for the D's. What about going from C to B? Well, you have to move right, right, down, down. So you were arranging these 4 items. 4 items is 4 factorial, but you have 2 R's and you have 2 D's, so we have to calculate what all of this is going to give us. So 7 factorial over 3 factorial, 4 factorial gives us 35. There's 35 different paths that will go from A to C. 35 different paths from A to C. If we calculate the number of paths from C to B, and you could probably count them by tracing them out, because C to B is only a 2 by 2 grid, we're going to have 4 factorial divided by 2 factorial, 2 factorial, which I think is going to give us 6. So we have 35 ways to go from A to C. And we have 6 ways to go from C to B. So if Bobby Bear had 35 different shirts and 6 different pairs of pants, you would multiply those numbers together to get the number of outfits. We're not multiplying shirts and pants, we're multiplying pathways and pathways. Bottom line here is we're going to have 35 multiplied by 6, which gives 210. So there are 210 pathways. That brings us to the end of permutations. We are going to be looking next time at combinations, which is a little bit different, a little more interesting too, I think, at times. Attached to your handout are 7 problems you can be working on. They all deal with situations where you have items that are repeated. Remember that you have to divide by the factorial of the number of times an item is repeated. So I hope that made sense to you, and I hope you have a great rest of the day and a fantastic rest of the week. We'll talk to you soon. Take care.